Hello everyone, welcome to our topic presentation for CNT 4165. Me and my partner choose the topic about advanced routing protocols for IoT and LLN, which means lower power and lossy network. Before we begin, we would like you to know more about us. My name is Elias Elarba, I am 22 years old, and I am currently an FIU international student. This is my senior year here at FIU. After that, I see myself working on a big company such as Google, Apple, or Microsoft. One thing that I would like to share with you is that I am from Venezuela, and it has been a dream studying here at FIU, since in my home country, we are living at difficult times to start a new career. I'm gonna share my personal email here in the slides. With my partner.
Greetings everyone, my name is Cameron Williams. I am 26 years old and I am in Florida International University as a full-time student. This is going to be my final term since I am a senior in FIU. Once I graduate, I might be able to work at Microsoft, Cisco, Apple, AT&T, Comcast, or the Sony company. One thing I can share about myself is that I was born from England and I was raised in Miami afterwards. My dream was to always study here at FIU, especially in the engineering department. My email is cwill283@fiu.edu.
Before we start talking about advanced routing protocols, I would like to say why we choose this topic. And the reason is because we realized that it is very important to know about routing protocols in the IoT file, since their purpose is to learn of available routes that exist on the enterprise network, build routing tables, and make routing decisions. At the simplest level, routing establishes basic inter-network communication, implements an addressing structure that, unlike, identify each device and organizes individual devices into a hierarchical network structure. In addition, the most recent trend is to see router as the integration platform for a wide variety of network enhancement such as security, policy, and service that extend the capabilities of IP to support telephony, video, legacy service integration, and other applications over a converged network. Routing protocols help computer networks communicate effectively and efficiently. Regardless of network size, these protocols can help securely transfer data to its intended destination. Understanding the different types of routing protocols can help you determine which type is the best to use. Lower power and lossy networks are typically optimized for energy efficiency and can be applied to industrial monitoring, building automation, connected homes, healthcare, environmental monitoring, urban sensor network, asset tracking, and more. Network devices in IoT are usually equipped with a variety of sensors and actuators, which from lossy and lower power networks and through various access networks with various technologies, they are connected to the internet in order to exchange information and share resources. Since the majority of devices in the IoT have low processing power, limited storage capacity, and energy constraints, it is very important to design standard protocols which can handle these features in the IoT. Also, the need for advancement in IoT network protocol is mandated due to the rise in number of physical things connected to the internet. In most of the routing protocols, flooding of route packets result in increase in overhead. The routing requirements of IoT LLN networks may vary according to the specification of the application. Thus, the role working group initially presents 4 informational RFCs describing the necessities for different groups of LLN. which are urban, industrial, home automation, and building automation. Urban lower power and lossy network applications have a number of specific requirements related to the set of operating conditions. The large and diverse measurement space of urban nodes coupled with the typical large urban areas will yield extremely large network size. Current urban rollouts are composed of sometimes more than 100 nodes. Future rollouts, however, may easily reach numbers in the tens of thousands to millions. One of the most important LLN routing protocol design criteria is hence capability. Urban are exposed to routing security threats that need to be addressed. The wireless and distributed nature of this network increase the spectrum of potential routing security threats. This is further amplified by the resource constraints of the nodes, thereby preventing resource-intensive routing security approach from being deployed. Also, this kind of LLN provides the network structure for applications executed in urban environments such as smart metering, pollution, and meteorological monitoring and general purpose for smart cities. Industrial. Wireless lower power and lossy network nodes in industrial environments are powered by a variety of sources. Battery operated devices with lifetime requirements of at least 5 years are the most common. Battery operated devices have a cap on their total energy and typically can report estimate of remaining energy and typically do not have constraints on the short-term average power consumption. Energy scaling devices are more complex. This system contains both a power-saving device such as solar, vibration, or temperature difference, and an energy storage device such as rechargeable battery or a capacitor. Also, security, monitoring, and control in industrial environments are some examples of applications supported by this group of lower lossy and power networks. Those wireless devices should provide easy installation and maintains lower power and high reliability. Existing industrial LLN applications have generally networked with 10 to 200 nodes. Home automation scenarios encompass a great set of applications such as energy conservation, consumption optimization, window shade control, and healthcare. Although the home automation application commonly use wired network and power-like communication. The use of wired networks can facilitate application expansion and possible upgrades. The routing requirements for home automation applications may vary according to the use case. For example, a healthcare home automation application requires a constraint-based routing with mobility support and lower coverage time. On the other hand, an alarm home automation application requires a network able to provide high scalability and coverage times. In this picture, we can see an example of home automation application. Further, the reliable support for different traffic patterns represent an indispensable feature for routing protocol in residential application. Concluding, a routing protocol able to support all home automation applications must be ready to provide constraints-based routing and support the mobility, scalability, coverage time, manageability, and scalability. Building automation applications include the monitoring of several aspects such as fire alarms, elevator system, control access, and intrusion detection system. Wireless devices can increase the flexibility and reduce the development cost of application. The network structure for building automation application should support at least 2,000 nodes, including sensor, actuators, controller, and user interface device. A complete building management system, BMS, can be composed from different a smaller application exhausted in several subnetworks that are connected through a backbone. Both the traffic pattern and the device density, as well as several other network peculiarities, and diverge for each subnetwork. Therefore, the routing protocols must provide a self-organizing structure with zero configuration to make the installation a replacement of device accessibility. Further, it must also provide scalability and support resource-constrained device mobility, addressing manageability, dynamic route selection, and security. In this picture, we can see how a building automation is built. At the end, during the definition of the requirements for the different lower POSI and lossy network types, IETF studied its existing standard routing protocols. The objective was to identify whether they could attend to the routing requirements of low-power networks. Also, the necessity of solving the routing problems existing in LLNs. Several extensions and new approaches have emerged. This study has the objective of presenting a survey of routing solutions that may be employed in network for IoT applications with lossy network and lower POSI network. Thus, only routing protocols for wireless network with support of IPv6 are considered. Moving on, we have these two routing protocols, LOAD and RPL, which are two of the major protocols that are standard and to be used in today's network. Their applicability, strength, and limitation are illustrated. The following aspects are especially studied, which are also of the great concerns of lower POSI and lossy network in constrained environments. The number of routing protocol messages used to maintain the routing table. This is one important factor in energy consumption, and a lower routing protocol overhead is thus beneficial to prolong the network lifetime. Also, support for different kinds of traffic patterns, which include sensor-to-route traffic, route-to-sensor traffic, and sensor-to-sensor traffic. First, we have RPL, which is a tree-based routing protocol created by the Role Working Group and defined by the ETF as the standard routing protocol for lower POSI and lossy network. RPL organizes the network topology in a destination-oriented graph, DAG, which is composed of one or more destination-oriented directed acyclic graph, which is named DODAG. Each DODAG represents a routing tree created by a root node, also known as a sink node or border router. In the RPL operation, the network node initially builds the DODAG. Thus, in the first step, the root node starts the process of DODAG construction, sending a DODAG information object message to its network. Also, RPL permits a new node to join the network at any time. RPL allows both upward from the node to its parent and downward from the node to its children routes. In this picture, it represents the traffic pattern supported by RPL. Lines with arrows indicate the traffic flow, while dotted lines without arrows indicate the links of the routing topology. On the other hand, we have LOAD, which means lightweight on-demand ad hoc distance vector routing protocol next generation, which is a reactive routing protocol based on AODV and adapted for LLNs. Similar to AODV, LOAD only creates a route when a node needs to send a data message to another node. The process of route creation, also known as route discovery, is performed to the use of control message adapted from AODV. The route request message is used during the route discovery process to find a path to the desired destination. The route reply message is used by the destination of route request to attend the received route creation request. During the route discovery process of LOAD, the nodes should store a set of information about the other node of the network. Thus, each node has a routing set, a pending acknowledgement set, and a blacklisted neighbor set. Regarding to this picture, we can say that in the part A, transmission of root request, message flooding all network nodes. B. Transmission of root reply and root request messages where both lines indicate root reply to message that are forwarded to the tab constructed by root request, and dotted line indicate messages that are optionally sent after reception of each root reply but not routed. And C. Transmission of data message through the path selected by a node after receiving root reply. After knowing the concept of each of these protocols of lower power and lossy network, we can see in this table that basic mechanism for RPL is proactive while for loan is reactive. Each of these protocols have their unique characteristic, while the only one that are the same for both is metric support. So you can take a look of this table and see the difference for each.
In terms of the routing solutions proposed for IoT, LLN are performed with the improvement of existent and well-known base protocols. Although several protocols have been used as inspiration, the principal and most recent approaches are based on the RPL and LoadNG. Some of those solutions are P2P communication, multicast communication, mobile nodes, different traffic and mode of operations, energy efficiency and QoS, and RPL objective functions. P2P networks are built on protocols that run on top of Internet protocols, hence why they were known as TCP/IP. Hence, P2P protocols are called application protocols or Layer 7, according to the model Open Systems Interconnection, or OSI. This means that P2P protocols require the use of other more abstract protocols in order to function, but that at the same time makes them easier to build and operate. Peer-to-peer communication represents an import of traffic pattern in LLNs, mainly in IoT scenarios. Although the default RPL implementation supports P2P traffic, the approach introduced by the IETF standard can be considered very costly in some situations. Also, P2P protocols have been widely used since their creation for different uses. Some legal, others a bit gray. But despite this, there is one thing very clear. P2P protocols are very powerful and allow the creation of decentralized structures, hardly objectionable and free to use. Many networks that inherently broadcast in nature, such as Ethernet or other shared media local area networks, and satellites can use broadcasting techniques to support multicast communications. The point-to-point networks may support it by using several point-to-point unicast communications. However, multicasting can be supported more efficiently as a logical multicast tree made up of switches or routers and network links. The multicast tree may be a rooted tree, where a source is at the root and all possible receivers connect to the root via branches or shortest possible paths between the source and each of its receivers. This works well for cases involving a few sources. For a large number of sources and receivers, the rooted tree may not perform well. Multicast communication represents a fundamental transmission type for several IoT applications. Thus, an industrial environment application running over LLN can require the sending of alert messages for a predefined group of nodes or base stations. To achieve this, the routing protocol should realize reliable multicast transmissions. In addition to multicast transmission, mobile nodes are usually powered by the batteries they carry. The Battery power is used for processing and wireless communications when using these nodes. Since the batteries have limited power, a node will die when its battery dies. Therefore, the battery power and energy consumption determines how long the node operates. In infrastructure-based wireless networks, when a node dies, there is no significant impact on the network topology except that its own service is interrupted. In infrastructure-less wireless networks, the problem is more serious since each node is a combination of source, destination, and router. When nodes die, the network topology changes, and the network may even be partitioned. The support for mobile nodes also represents an important task for the majority of applications in IoT environments, mainly in urban and industrial scenarios. Thus, an efficient mobility support protocol should provide fast, continuous, and reliable communication among mobile and static nodes. IoT LLN applications can require the use of different data traffic patterns during its execution. As an example, two nodes can exchange messages among them, creating P2P traffic, and a few moments later, both need to send data to a central node generating MP2P traffic. Furthermore, the central node can send data messages to a specific group of nodes using multicast communication. Thus, based on this requirement, the routing protocols should provide support for different traffic patterns, preferentially permitting that all these can be used simultaneously. IoT and the energy efficiency market are huge, especially for end users and integrators. IoT will allow end users to measure, check, and quickly adapt their installation according to the expectations of the market, the cost of the raw materials, or the energy prices. For energy efficiency system integrators, IoT will improve their capability to address customer needs, rapidly reducing the time for integration and commissioning. Integrators will improve the maintainability of their systems using remote diagnostic and fixed capability of products, reliability for data message sending, and acceptable latency are requirements for all IoT applications. Due to power restrictions of various IoT devices, it is required that the packet sending task can be executed with the shortest energy expenditure possible. Therefore, a feasible quality of service and reasonable energy consumption are considered as the most crucial features for all routing protocols for LLNs. RPL uses objective functions to construct the DODAG. Objective functions is also used to define the rank of a node, which is a node's distance from a DODAG root node. RPL determines the whole topology by building the DODAGs within instances, where each instance is associated with a specific objective function. Objective functions combines the metrics and constraints to find the best path. However, RPL's main specification has no default objective function. Therefore, OF0 is designed as a default function that is common to all implementations and provides interoperability between different implementations. The RPL protocol uses objective functions to determine the network topology and the process of preferred parent selection. In terms with the explanation with the data table, the studied routing solutions for LLNs are, in general, based on the RPL routing protocol. This is justified due to RPL being an already consolidated and well-known solution. Furthermore, RPL can initially better attend to the routing requirements presented by the IETF when compared to other standard routing protocols. Furthermore, some approaches use solutions based on the combination of RPL with other already existent proposals. These approaches seek to solve the RPL drawbacks with the benefits of other previously known proposals. Although these approaches can improve the standard RPL, the final algorithm tends to be long and complicated, requiring a higher storage and processing capacity of the nodes. Energy efficiency and quality of service are requirements of the majority of IoT applications. Thus, LLN routing solutions should provide reliability for packet delivery with low latency and efficient energy consumption. Also, the main constraints of the current routing solutions are the increment of algorithm complexity, the extension of message length, the increment of the use of control messages, and the implementation overheads. Since the definition of LLNs, the routing in the networks with low-power devices is considered a significant challenge. Seeing the importance of studying appropriate routing solutions, IETF created the World Working Group. Initial conclusions of a study developed by the new working group showed that the existent IETF standard routing protocols were unable to provide the routing requirement of LLNs. Thus, ROLL began the development of a new routing solution considering the specifics identified by the group for different LLN applications. Although the ROLL working group has defined RPL as the standard routing protocol for LLMs, several works have shown that the solution presents severe limitations and drawbacks. Thus, various new solutions studied in the course of this document have emerged in recent years trying to mitigate the existent routing issues. Thank you.
Here are the references that we use to guide ourselves to know more about this topic. If you would like to know more in depth, we invite you to open one of these links. They are very helpful. Thank you so much for your attention. If you have any questions, please feel free to leave it in the comment box. Thank you.